basic properties of biomaterials. This is what the syllabus says for GATE BM, GATE Biomedical Engineering paper. Basic properties specifically are ceramic polymeric composites, right? Properties, there are many properties that every year, this mechanical properties. How strong is something? Strong is a material implant compared to the bone, right? How stiff is a stent compared to the surrounding artery? Questions like that are of extreme importance because success or failure of a specific application is governed by that. Mechanical properties primarily govern, success or failure. So the sigma equals A epsilon, the mechanical properties, the stress strain curve, right? Almost every year there is a question from that. And then there are some miscellaneous questions. There are many other properties, but almost every year, there is a question from stress strain curve or this initial typical linear part where the stress is proportional to strain. And then we have the second major topic, fundamental characteristics of implants. In a application, put it, will the application succeed or fail? Will the implant work or not work? Stent, be it, dental clipper, whatever it is, orthopedic implant. If you put it, is it going to work? And some of the important characteristics that we are concerned of. What is the biocompatibility, bioactivity, and degradability, right? These details show up over there. Fundamental characteristics, the design aspects that make or break a given application. And this is highly, application specific. Can tell you two things. Is go for the applications that are quite prevalent. They aren't looking at typically some extreme, very rare application. Most prevalent cardiac applications, coronary stent, wall, right? Orthopedic implant, bone implant, dental clips and things like that. Dental clipper, dental amalgam, bone cement, things that we use again and again. Yes. That is where again questions show up from, and what you need to look for is the design elements that make or break a given application. Is highly application specific. I'll show you a couple of examples today. And here, if I have to highlight one topic, this is biodegradability, because the first order transient video, most important gate topic, not just gate biomedical topic. Topic is this first order transients, right? Biodegradability, to some extent even bioactivity, many of the things that kind of mentioned here, right? Drug delivery, basics of tissue engineering. Many of the systems, first level of modeling or approaching that system is a first order simplification. So there is typically a question involving some kind of an exponential curve fit. Just like almost every year there is a stress strain question. Almost every year there is an exponential question. And for non-biomedical students and doctors, actually these questions, non-biomedical and students and students are other than doctors, like instrumentation electronic students, this is not that hard. Notice some of the ways that you model diode is also has a kind of like a exponential relation, right? Or simplest RC circuit transients, that is the simplest examples that you are most used to. So there is almost every year there is a question from exponential decay or a kind of exponential curve based on question. What I notice is it typically shows from biodegradability or a concept surrounding that. And then we have the next topic. This is characterization. Almost every year there is a question from characterization. How do you characterize? If you say there is a property restriction, how do you measure that? Right? What other properties? In fact, many of the things, biocompatibility, bioactivity, how do you actually do that? Right? Pathology, how do you look at cells? How do you look at tissues? In fact, you can go scales, smaller than that. How do you look at, DNA function and things like that, right? This characterization techniques. And again, this is a ocean. Fortunately, they have mentioned a couple of techniques over here, and they also seem to stick to those techniques. What is again given here can be kind of made atomic force microscopy, can be made in ocean. And then there is electron microscopy, transmission electron microscopy, and then there is FTIR, right? But so far, what I notice is they are kind of sticking to this. The techniques mentioned here, questions are kind of concentrated here, although there are hundreds of characterization techniques. So that makes your life easy. And here, many of the things that we learned in biofluid mechanics, right? Ability to measure, characterize viscosity, rheology is essentially that. So for today, again, I'll give you the bare minimal things that you need to know about the rest of the techniques that is mentioned here and what they typically ask from us. So characterization techniques, fortunately, this is a small subset, and what you need to know there is also like very relatively well known by now. So characterization techniques, and there is one more subset. This is where your core the knowledge will really be tested. Here, these questions, it doesn't matter, whether you're prepared for the gate exam or not, but it actually tests you whether you really know that subject specific, domain specific knowledge. There are many miscellaneous questions here. If you are lucky, if the question is from your domain, you can answer that. Else, some of these miscellaneous questions are kind of hard to answer. Again, I will show some examples from PYQs that I have. So miscellaneous. So the agenda for today is to show you the typical questions that show up. The way I'm going to do that is, of course, look at GATE biomedical PYQs. I'm going to look at PYQs from 4 years, 2020, 2021, 2022, and 2023. And I'll not just look at the question and like kind of answer the questions. For both theory questions as well as numericals, I'll try to discuss bare minimal things you need to know, bare minimal theory and concepts you need to know, any formula that you need to typically. And there isn't a lot, but whatever you need to know, I'll try to introduce that. I'll solve this PYQs, and then typically I'll try to, first of all, the questions are already clustered. And for each question, I also, if possible, they can ask you this, they can ask you the same question in this way and all that. Okay. We'll also have the discussion. So that's the agenda right now. Let's get started. Get biomaterials. I have all the questions in sequential order. They are kind of clustered based on topic and the type of question. So there is some kind of a structure or order to this discussion. First question, some basic theory questions. Biomaterials with shape memory effects are not used, and we have 4 options. Can we quickly get some guesses or possible answers? Great. So many of you are kind of prepared. Many of you say this is C. We have shape memory effects. Typically, this is nickel titanium alloys, right? And if you think about nickel titanium, there are kind of 2 effects. One is a shape memory, and then there is this super elasticity. And typically, wherever is important, dental arch wires, your teeth is looking some way, and then at the end of the day, you want to kind of like correct the teeth, right? Layers that you are putting in should eventually actually, or preferably in the shape that the teeth should eventually take, the tooth should eventually take, right? Wherever applications where the shape is important, and often it requires just if you have that the application, the right shape, even that's not the question. Actually, the question is perturbations to shape. You kind of perfect, you kind of cringe it, crumple it, and all that, but still there is a preferred shape for the implant that you are putting in. Basically, applications like that, shape memory is extremely useful. I'm not going to get into details of what shape memory is, what super elasticity and all of that. But to quickly give you a point, intracranial aneurysm clip. This is intracranial inside the head. Let's say there is some kind of circle of Willis or something like that. The way, say, one of the parts is bulging, you're going to get the stent over there, right? The stent is going to be compressed form so that it can actually take it most places in the blood vessels, typically most of the arteries, right? Be it a stent, be it an aneurysm clip, right? It's in a very, very, very compressed shape so that you can actually take it to the place of interest through some kind of minimally invasive approach. You're going to enter an artery somewhere, you're going to put a catheter, take that stent. While you're taking the stent to the location of interest, the stent cannot be really big. It needs to be really compressed. It needs to be quite compact. But once it gets to the right place, you can kind of like, if there is a preferred shape that it can get into, you really need that feature. That's why notice any type of aneurysm, that is most blood vessels, typically most arteries, aortic aneurysm, beta, stent, coronary stent, intracranial aneurysm. This shape memory is important. Again, arterial blood vessel closure devices. This kind of gets important. Dental archware, we know at the end of the day, or at the end of the treatment, teeth shape should get corrected, right? There is a preferred shape. The preferred shape, and the implant you are putting in is robust to perturbations. Robust, first as in like you kind of crumple it, you kind of strain it a lot, but still can actually get back the preferred shape. This is robust to shape perturbations. There are many other perturbations you could do. I'm specifically looking at shape perturbations, robust to shape perturbations. If you crease a paper, it's going to be very hard to kind of like uncrease it, right? But still, if you notice, actually, if you take the paper or like a rupee note or something like that, if it's kind of crumpled, you can iron it and reasonably get back the shape. Underlying that is essentially the shape memory effect, because this rupee note preferred shape is that plane, right? Quality dresses, wrinkle-free cloths to some extent have the shape memory effect. It's not just nickel titanium alloys. You kind of heat it up and it kind of goes to that preferred shape, right? Here we have this aneurysm clips, stents, and all that as its preferred shape, and they are quite robust to shape perturbations. That is, you perturb the shape a lot, but still there is this preferred shape that you can easily get that to. Only by heating, right? Body's preferred shape typically happens at the body temperature, right? So, and you have to engineer it. You have to design the material so that based on the application, that preferred shape preferred shape fits with the environment and temperature and things that you put it in. That is one thing. This is quite robust to shape perturbations, and that's where we have this shape memory effect. Orthopedic total joint replacement, this is just a mechanical support. You don't need and typically minimally invasive orthopedic joint replacement, hip arthroplasty and all that, there isn't minimally invasive. You have to make you have to cut the bones. So what matters here is the strength, not the shape. The stress strain relations is what is more important here. And the strains involved, the shape changes involved are actually very less. The strains are too low in this application to in fact even consider the shape memory effect or even super elastic effect. Here strength matters, rest of the application shape matters. So that's a quick comment on this question. Let's go to the next question. Which of the following mechanical prosthetic balls were invented as a replacement for disease heart balls? So if you look at this question, most of the balls actually do exist, but not all of them were invented for, right? I think the important word here is most of these balls are all there. If you say, for example, if you take a car engine, most of these walls are there, but the walls that are specifically invented for disease hot walls, I think this is ball and cage, bi-leaflet wall. This is where some basic biomedical literacy on what kind of walls they put in, right, and what kind of evolution of walls kind of happened. It's kind of useful, but this specific question, I think globe wall and all that is there in mechanical systems, that is car engines and things like that. Fairly easy. Let's move on. Now, a couple of notice application specific or domain specific questions. If you put a bone implant, right, which of the following may cause failure of bone implants? So they are talking about biocompatibility, bioactivity, and things like that, right? For bone implants, there are some typical failure modes that you're trying to address by designing that implant. And what is given here is a term and in fact a description of what the term is. They have really made your life easy by not mismatching the term and the definition. Stress shielding actually does mean reduction of bone density due to removal of typical stress from bone by an implant. Aseptic loosening does mean loss of bond between bone and implant in the absence of an infection. The term and the definition do match. All you're supposed to do is which one of these are actually failures, right? So fretting fatigue, by definition, is progressive deterioration of material by small scale rubbing. Then osseointegration, formation of direct interface between an implant and a bone without intervening tissues. Which of the ones are correct options here? This I suppose is a MQ, multiple select. If the implant is too strong, right? There is no job for the bone. Notice movies with who are too strong. Typically, they are very interesting. Movies with heroes who are too strong, they can address any aspect. It's hard to find a good movie that way. If they can solve issues easily, problems easily, then where is the story, right? So bone is supposed to do the work. Implants are supposed to aid the bone. They cannot overshadow the bone, which is essentially what happens in stress shielding. So that is actually a failure bone. Aseptic loosening, absence of infection says aseptic, fine. Loss of bond between bone and implant. Yeah, if the bone and implant doesn't bond, actually this thing fails. If there is a gap, there is a crack, slight movement here and there, and then there is failure. There's an issue with stress strain propagation, right? Transfer of stresses and all that, transfer of forces. So things cannot loosen. Fretting fatigue, again, this is essentially small scale rubbing, material degrades, then starts corroding. Don't want that. Osseointegration actually is something that you really want, right? The bone implant that you put in should actually bond well with the bone, and preferably it should form a direct interface. So this is something. This actually is what should happen in implants that succeed, right? So rest of them are, you need this for success. Rest of the things, of course, are failures. And this is where I mentioned there's somewhat of a miscellaneous question where there are questions that are very application specific. If you have kind of worked in this field, you kind of know this very, very well. And typically notice orthopedic is quite ubiquitous. And then comes cardiovascular applications, which is where we have the next question. Ideally, coronary stent should. What are the design aspects of consideration? Clotting, of course. The point of putting a stent, typically, there is a plaque that ruptured and then kind of like partially or fully obstructed, right? Or there is stenosis. It should be thrombo-resistant. It should be clot-resistant. Fine, that's what you want. I'll come to B and D in a moment. It should be fatigue-resistant. The stent, this, if you look at it, the heart, the beating heart, right? Every pulse, the stent kind of deforms along with the heart, right? Stent inside an artery, say this is which is a lumen. So this is a lumen, half the lumen, you put a stent here. Every beat, the thing kind of like constricts, right? You do this again and again and again. You don't want that material to fail, right? Failure due to repeated loading. A good example that I gave us, hey, International Space Station, although it is there floating in the space, there is repeated thermal loading. Get exposed to sun, not get exposed to sun. Get exposed to sun, not get exposed to sun, right? Over the course of year, this happens again and again. Thermal expansion, contraction. Of time, this happens, right? Thousand essentially like 3 years, couple of years, right? This happens. The cracks, small cracks form. They get bigger and bigger. Eventually, ISS cannot be functional. In fact, notice this is failure due to repeated thermal loading, but typically failure due to repeated loading, mechanical loading, is what is termed as fatigue. And this what stent you put in, there is repeated cyclic loading because of the pulsatile heartbeat, and you want to avoid that. So fatigue resistance is important. And one of the problems that the moment you put in a coronary stent, the real problem is this stenosis, restenosis. You put a stent because there was a stenosis, there was this closed lumen, and now tissue is growing on top of the stent that you put in. Intimal hyperplasia, right? So you don't want this. There is this lumen, it kind of like partly closed. You kind of open it up. You don't want it to close again, either due to a weak stent or due to strong growth in and on top of the stent, right? Which is what happens if there are this smooth accumulation of smooth muscles and then deposition of extracellular matrix. These are highly indicative of restenosis, which you don't want to happen. For that reason, coronary stent should not promote smooth muscle cell accumulation, should not support deposition of ECM, SMCs and ECMs. Again, this is application specific. The answer here is AC. Orthopedic, there is a cardiovascular application. Notice this is also a cardiovascular application. And what we have here is a orthopedic application. And typically, and then there is this dental application. Dental application, perhaps something that, they have to revert back to these applications. one of the applications they have, important application they have missed so far is dental. So again, manders and success and failure of a dental application, that is something that I would take a look. Now let's get back to the next question. Equipment that measures. Now here we come to characterization techniques. So in fact, what we have seen so far is not really miscellaneous. Design elements is what we have seen. Most of the questions that we've seen so far is actually from design aspects, some basic knowledge, right? These are all design aspects regarding the stent and all that. Now let's get back to characterization techniques. Second important topic. Here, one that measures elasticity of blood vessels in vivo. Yes. In answer along with concise supporting explanation or description. Rheometer, rheology, viscosity, rheology, fluid properties, specifically viscosity. Thermomechanical analyzer. Any of the polymers and all that, properties of polymers, mechanical, chemical, physical properties of polymer are highly temperature dependent. So you want to analyze mechanical properties and thermal properties together, or mechanical properties as a function of temperature. A bone cement, for example, right? Those are best analyzed with thermomechanical aspects or characterized with thermomechanical analyzer. Very simply, dynamic mechanical analyzer. This is repeated loading, typically viscoelastic effects, right? Cyclic repeated loading. These properties are tested with a DMMA, dynamic mechanical analyzer. Again, sort of a cyclic or a repeated testing, but this is still mechanical. And equipment that measures elasticity of blood vessel in vivo. You're not going to use a rheometer inside artery or something like that, surrounding the artery typically. Thermomechanical analyzer, again, not the place. Dynamic mechanical analyzer, actually you can do some sort of advanced ultrasound to get mechanical properties. You can put a catheter, some kind of sound data and all that, actually you can analyze and get some mechanical information. But what they're referring to here is, what they're expecting you to know here is, there is this thing called, there is a way to measure pulse wave velocity after Bowen's T-wave. Where I also gave this analogy and all that, right? This already showed up in your discussion, right? What is this? You have this pulse wave velocity is E T by ET by rho d. Rho d, whatever it is, right? Whatever makes it easy to remember that. Notice. Plus diameter, even pulse to extend, you need to know, you have to measure the pulse at two places. You need to know the distance between them. In addition to that, you also need to know the time delay between, occurrence of two pulses, right? Many of this depend on your ability to measure dimensions, right? So the bare minimal thing, this is not actually a dimensional analyzer, is sort of, you have some other imaging mode where you can measure the dimensions, ultrasound or something like that. And then that, notice, once you measure this is typically known, rho is known, you can estimate or infer what E is. The rest of the other things in this equation is known, right? So you can get an idea of what the stiffness of the blood vessel is. So due to that, the correct answer here is, some of you said, this is dimensional analyzer. The dimensions, actually, many of the other things are fairly easy to do. Of course, this is somewhat involved. You also need to know the time delay. This pulse wave velocity. Someone is asking, what does the C refer to? I suppose this C, not this C, right? C that I wrote here refers to pulse wave velocity, the speed at which pulse is traveling in the blood vessel. Sound is a wave, it is traveling the speed of sound, right? So pulse also travels like a wave. That is, it's best modeled by a wave, or simply modeled by a wave equation, right? And the speed at which that wave moves is the velocity, the C that I have written here. So let me also write down, typically this is, just give me 1 second. Mechanical analyzer, notice this actually gets important in terms of it's again important in terms of something like bone cement and things like that. Temperature, thermal properties are important. Where is this transition temperature happening? It may not be in fact a strict first order transition. Where is this transition from, where is this phase transition happening, and all that questions be addressed using a thermomechanical analyzer. This is dynamical mechanical analyzer. You are typically doing some sort of repeated loading, repeated or cyclic loading. And this is typical because, there are other dynamic things that you can do. Now, the first question, as you notice, the cell, structure kind of maintained by this phospholipid bilayer, right? For it to be stable, there has to be a hydrophobic part and hydrophilic part, right? That is something, whether something is hydrophobic or hydrophilic is very, very fundamental physiology, right? Again, for something to be biocompatible, the basic question is, hey, is it hydrophilic, hydrophobic? That is a starting point. Water will stagnate there so that some kind of corrosion will happen, or like, no, it kind of repels water. Because water, what else? Perhaps something, it's philic to something else, right? That's a very basic question. Here they have just given you water with contact angles, surfaces A and B, theta A, theta B, or the contact angles based on the figure, which of the statements are below is to. They want to compare, or they want to identify hydrophobic and hydrophilic surfaces. Notice, surface is well embraced by that water droplet. Actually, a quick pointer here. Water, if you put it in a beaker, it has a shape. If you look at a droplet, right, it has a different shape, and that shape is specific to the surface that you're putting in, right? So this is one place where you can see, not saying, that properties that we take for granted, properties like shape, the way they change just based on length scale, right? Even properties like color can change based on length scale, right? Gold looks like gold, in our length scale. If you go to slightly smaller and smaller scales, gold can start looking black, for example. The properties can be drastically different just by changing the scale. And this is a good example. So this is quite embracing that the surface very well. This is not like all that friendly to the surface. It's not all that gelling well with the surface. Not a very deep hug. I'll give a handshake. This is sort of a handshake. Water likes one surface a lot, another surface, fine, for formality, I'll do something, right? So A is more hydrophilic, surface B is hydrophobic. That's correct. So most of you got this. This is embracing this quite well. Sir, where is this hug? I am not able to see the hug, right? Perhaps if I put a couple of eyes here and put draw arms here and all that, you can easily see that, but like kind of open to that surface. This is not that open to the surface, which is what I'm trying to do. Basic property, hydrophilic, hydrophobic. And so typically we also we may need a demarcation, right? This angle is a lot, 60 degree. Perhaps at 90 degree, we can put a demarcation. Anything above 90 degree is like somewhat hydrophobic, but it's not a very strict demarcation. Smaller theta A contact angle is less than theta B. In the side, you have hydrophilic. In the side, you have larger angles here, hydrophobic. Move on to the next one. This is a miscellaneous question. Biomaterial formation of hydrogen bonds and alcoholic groups will lead to a shift in IRP current. Say you're used to using a FTIR, Fourier transform infrared spectroscopy, almost using that every day, and use it to see whether alcohol is there, whether what kind of chemical structure is there. If you have that kind of domain specific experience, you are likely to answer this. In this case, the broadening of IR peak happens. OH alcoholic group oscillations happen at 3,500 centimeter inverse. You could partly do this from recall. I may partly recall this answer key. Those who could really answer this is those who are using this FTIR day in and day out. You're working in a characterization lab. You're likely to answer this. But having said that, I wanted to actually have a summary of which chemical group typically shows up at which infrared wavelength, or this is wave number. I wanted to have a summary table. Right now, I don't have it, but again, that is something that I can add in the post. I'll do that, and I'll try to get you that information here so that, when you're facing or looking at it just before the examination, you will have that information at one place. Right now, I don't have it, but I'll add it during post-processing. Fine, let's move on. A water insoluble polymeric biomaterial can become water soluble. Water, again, this is in vivo by which of the following mechanism? Water, this is polar. You have H2O water. There is a tendency for this to have a positive charge. I suppose there is a tendency for this to have a positive charge. I suppose I remember this correct, and there is a tendency for this to slightly more negative. I have the signs correct. There is a tendency for this. This is a starting point of all this molecular attraction and things like that, right? Hydrogen bonding. Water is polar, that is, entire molecule doesn't have a charge, but the individual parts of it behave as if they have a charge, or there are directionalities, there are location dependent positive negative preferences in the structure. So this is polar, and typically if something is polar, something is like again has a preference towards, if there is a location dependent preference for charge, right? Electron likes to stay at one place or compared to some other place in the same molecule, that is likely to bond, uh, you know, those are likely to bond very well with these. This can be from some other element, some other atom, some other element. These are likely to bond. In fact, they can bond hydrogen, oxygen, not necessarily, but typically there is hydrogen bonding. That is predominant. So something that is polar will bond. Oh, we have a question. What is the meaning of cleavage? It's like, I think cleavage put in this concept, I think is fairly straightforward, right? Out of context, perhaps there is a confusion, but this is like crosslinks are getting cut, right? So at the end of the day, if you make cuts that create polar groups, it's likely to become water soluble. So cleavage of crosslinks between, for example, I'm going to like break this. This is a molecule. This is not really the type of cleavage they are talking about. There is R, typically written this way, right? N times, right? So if this polymer bond is kind of cut, cleaved, right? That is what they are referring to cleavage. And cleavage of crosslinks between water soluble polymer chains. Yeah, they are already water soluble. You cut them up and they are now free, right? Because of the cut, water soluble things get more exposed. It's going to, these were kind of inert because of the bond, because of the crosslink, because of the cut. Now they are open for interaction and they are water soluble. That will make the polymer water soluble. So this is correct. For the cut, because of the cross link or the bond, right? Cross link is this is a polymer chain, and then this is linked with here and there. It is kind of linked with some other element, right? So cross link, not just a single chain, but the chain, there are cross connections in the chain. If one of them is cutting that, because of the presence of the link, the parts here are kind of inert. They are not free to interact. The moment you kind of release them, cutting them, now they are free to interact and they become, of course, they are polar, they are water soluble. The entire polymer gets water soluble. Cleavage of side chains leading to formation of non-polar groups. Non-polar groups, water is not going to interact with that. So this is, in fact, whether you end up creating polarity or not, that's a question. So this is not a correct answer. Non-polarity doesn't help. Water, hydrogen like to bond with something that is polar. Cleavage of backbone linkages between polymer repeat units leading to formation of polar groups. Again, at the end of the day, water soluble is typically, this is polar. Forming more polar groups, it becomes soluble. Enzymatic degradation of crosslinks between water soluble proteins. It doesn't matter where the polarity, again, this is also water soluble, it's polar. It doesn't matter where that polarity is coming from, by cutting, degradation, right? Cleavage, cutting, crosslink, backbone, crosslink, water doesn't matter. But if you end up creating more polar or water soluble groups, it's going to be more water soluble. That's it. So at this stage, I have one more question. Sir, will they ask questions from hydrogel? So actually, my BTech project happened to be something on hydrogel. Actually, more a complicated version of hydrogels. Can we have here is actually a question on hydrogel. A polymer, what makes its interaction with water special or interesting? It or polymers that have interesting interactions with water. Very roughly, that's a hydrogel. And what you're talking about is essentially properties of a hydrogel. So they can ask questions from hydrogel. In fact, they have already asked questions from hydrogel. Sir, will they ask questions from hydrogel? Yes. Example, this one. Let me also point out, also asking numericals. Towards the end of this, we'll discuss thermal expansion. If a material can expand due to temperature, it can also expand due to pressure or water pore pressure. water pressure, hydrostatic pressure. So for that reason, almost you change the context here, change a couple of temperature with water, bone cement with polymer and things like that. You can reframe this question as a hydrogel question. Okay, so you'll get back so you can have numericals. That's also an example of hydrogel questions. And where this is coming from really is essentially properties of basic properties, sigma is epsilon stress strain curve. There are some miscellaneous properties. Notice polymer, specifically interaction with water and all that gets interesting. That's why they have put it up there. Just it is sort of a miscellaneous question. And this is a characterization question. This is sort of a property question, somewhat miscellaneous. Kind of gels well with the hydrogel concept, but somewhat miscellaneous stage. This is hardcore characterization. Match the following in the context of biomaterial. They are being very explicit. I am asking you a biomaterial characterization question. Can you match surface characterization technique with phase property that can be measured? So you have scanning electron microscopy, Fourier transform infrared spectroscopy, X-ray photoelectron spectroscopy, atomic force microscopy. There you have elemental composition plus functional groups, topography. There could be a lot of confusion on some of the things like some of these techniques based on your expertise and your skill level. You can use, in fact, just one of these techniques to pretty much measure any of the properties mentioned here based on your skill level and expertise. But what is typically used? That is a question, and then there the easiest just FTIR functional groups. We kind of already saw that alcoholic OH group. Where is this infrared peak happening? So that I can see that in IFTIR, right? Infrared Fourier transform, infrared spectroscopy, right? Typically, FTIR is very good at because all the molecular level vibrations and oscillations, energies involved or at the wavelength or wave number corresponding to this infrared region. Molecular, the bond energy is be it like stretching, this kind of expansion, even like twisting and all that. Those energies, molecular energies, or the wavelength of infrared, or has energies corresponding to the infrared region, right? Given the wavelength, you can calculate the energies, right? This is why with functional groups, the energies involved or in the infrared region, many of the energies of interest. It's easy to identify this group, and typically each group has a very specific signature oscillation or a vibration or a dynamic mode. For example, OH group that 3500 centimeter inverse, right? Again, so these oscillations can act as signatures, and you can easily identify a chemical group. So for that reason, in fact, before I see that QM, this is the only option, I'm going to choose that is what I would have done in the exam, because the easiest match here is the FTIR functional group match. There can be some ambiguity in matching other things, but now that I think we have found the correct answer. So let's go match a scanning electron microscope. This you typically get L. You can get roughness. Notice, hey, I can get roughness from atomic force microscopy, right? No, I'm going to use atomics. You can get atomic force roughness from atomic force microscopy. They are using scanning electron microscopy for topography. Hey, what is the difference between topography and roughness? It's very subtle, but somewhat ambiguous. It's not clear based on this match. Notice, in fact, what I have drawn in gray is a somewhat of an ambiguous map, but we can see that because we have already found the correct answer. Then this is RK, X-ray photoelectric effect. You shine light, you knock off electrons. So, typically inner shell, outer shell electron, you manage to knock off some of these electrons by shining light. And if you knock an inner shell electron, of course, that vacant spot will be occupied by a energy, a higher level. Yeah, I don't know whether I'm going back to Bohr or like how old this is. But this very, very, very old orbital view of this atom, right? If you knock out an electron here, it's going to be occupied by typically one of the outer shell electrons. And these transitions are very indicative of the energies involved and can act as atomic signatures. I said molecular vibrations can act as functional group signatures, right? Here, sort of electron dynamics, right? Electrons are transitioning from outer to inner and all that. Those has signatures of elemental atomic signatures. So you can easily get elemental composition. So in fact, RK is also a reasonably good match. Based on that, we kind of ruled out this, right? And quick recap, this strictly have here is, let's kind of even zoom this, but here I have a summary of characterization, right? And specifically the summary is how does electron interacts with the matter you are shining it at, right? You have an electron beam and then you have the sample, and then there is interaction. And there are many types of interaction. Based on that, there are many imaging modes. A quick summary, you've got auger electrons, characteristic X-rays, EDX, cathode luminescence. Then you have secondary electrons, backscattered electrons, continuum X-rays, that electrons that kind of break and all that Bremsstrahlung. And somehow that electrons and kind of manage to through the sample, typically a thin sample. Then this side you have inelastic scattering, elastic, incoherent, inelastic, elastic scattering. There you got transmission, electrons that got transmitted. There are different types of scattering that is happening in the other side of the sample, typically if it is two. So there are many aspects, type of bounce back that happens, interaction between electron beam and the sample. If you throw a ball at a wall, you're going to get back the ball. Sometimes a lot of loading repeatedly doing this. Rubber ball, there can be fatigue and it kind of you kind of get a toned ball. But if it's a tennis ball, typically you get back a tennis ball. That is not the case with an electron. You throw a ball, now you have this, you can get many things back, right? And each of them carry signatures on what the ball is made up of, roughly. This has information on this. And what you need to know, do you need to know what all these are? Not necessarily. Essentially, you can do transmission electron microscopy, and then you can also get backscattered and scanning electron microscopy, typically at the top. Scanning and transmission, those are the two takeaways from here. So there is scanning happening at the top. Scanning can happen with transmission also, but how should I? In fact, there is scattering happening, then there is transmission happening. What is more important to know? Yeah, fortunately, I have this table. List of characterization methods and their capabilities for microstructural analysis of materials. You have optical microscopy. You can look at the grains and all that, say in an alloy or metal. Grain structure and all that can be seen with a very powerful optical microscopy. Some of the grains are in fact sometimes visible. So optical microscopy should do that. Morphology, you can get that information. Electron microscopy. And then please let's write down what is what. Transmission, electron through it. I don't need all of this. Transmission, electron microscopy. This for the first time, let me electron. Why do this? Light is a physical restriction, typically diffraction. There is a resolution below which light is not useful. Electrons, how about electrons? They can surpass that optical limits, right? So you can get better resolutions at the starting point of electron microscopy. You have transmission, electron microscopy. Then you have scanning, electron microscopy. You have STEM. Suppose this is scanning microscopy. Then you have atomic force microscopy. Some of these are okay. Atomic force microscopy. Then you have X-ray, XRD, X-ray diffraction. I think one of the first and best features of DNA, right? Kind of obtained by a scientist, but Nobel Prizes were awarded for some other scientist who kind of made sense of the data published by the other scientists, right? Watson and Crick. So that was done with X-ray diffraction. Structure of DNA kind of like was done with X-ray diffraction. So you have XRD, FTI or Fourier transform infrared spectroscopy. That I also have that here. The difference between these two things, again, I have to do this reasonably fast. Electrons can get transmitted. Electrons can get scattered and bounce back. That's a difference between scanning and transmission. And then you have scanning tunneling. You can also put a probe. You put a probe in AFM. This typically has a probe that you can kind of pass near a sample, right? A tip, like I have a pen tip, right? You can use a probe to actually try to see where things are, right? Try to see where things are. Scanning tunneling also uses a similar probe. And what starts mattering is not whether electrons can transmit to the other side of the sample. What matters is whether electrons can tunnel the gap between the probe and the sample. So here also a probe is typically used, and what matters is whether electrons can tunnel between the probe and the sample, right? They can only tunnel here. That is quantum mechanically jump from seen from a classical point of view. There is no way that electron can actually go there, but there is a quantum mechanics says there is a finite probability, and it does happen. That is tunneling. So these two have a probe. In atomic force microscopy, you're going to typically see how that probe is bent, and scanning tunneling, you will typically see this flow between the probe and the sample. And I have also kind of summarized what you can use for what crystallography, morphology, and chemical structure. And the summary is kind of more than enough for most of the questions that they are kind of asking you. It's not necessary to know this, just be aware there are many types of electron microscopy that you could do. The bare minimal things you need to know are kind of summarized here. Given the interest of time, so I'm going to skip this. And I also suppose I had this probe and picture at the right place. Back to normal size. Yeah, I hope that I had the probe and the details I have here at the right place. Let's move back. Backscattered electron detector of scanning electron microscopy is used to. From what we see, can we answer this? Electrons are getting backscattered. Phase topography of the sample. Quantify surface roughness. No. Measure atomic number. Backscattering actually it is somewhat, there are signatures of the atom in the backscatter, but that is best seen in any photoelectric characteristic lens, right? So backscattered, you don't get atomic level information. It's not backscattered light. This is backscattered electrons, right? What you can differentiate is, hey, different chemicals are going to interact with the elements differently. This is fairly easy to do. And, it's very hard to get atomic information from a backscattered electron. Backscattering is going to depend on, the angle of hit, where the atom is and all that, right? The atom is oriented in the sample, in the molecule and all that. But notice chemical composition, if you're trying to contrast, the region is fairly broad. Any of the details that would otherwise matter, angle of hit and all that, kind of get nullified. Effect of them are kind of not seen. Yeah, if you can measure light, energy, if you are like measure light, that has signatures of that, that has atomic signature. Whichever angle the light is coming out from, or whichever angle the electron is hitting the atom and the light is coming out from, it has a signature transition energy values. That's not the case with scattered electrons, right? Yeah, so here D does best. Roughness and all that you'll rather do with AFM or something like that. All right, let's move on. So we have a few numericals. No, we have the stress strain curve. So we also have some theory questions, but we are heading into numericals. Polymeric scaffold has been developed for cartilage tissue engineering to understand the biodegradability of the material. This polymeric scaffold with a dry weight. Notice there's a question from biodegradability, right? You had a scaffold and a dry weight of 20 milligram. You put it in a lysozyme solution for 7 days. End of 7 days, scaffold is freeze dried. Dry weight is measured to be 18 milligram. You put in 20 milligram. The change, what is left is 18 milligrams. The degradation is the extent of change, and specifically extent of reduction. What is important here is degradation. They are not asking you the change in weight of the polymeric scaffold. They are asking you what is a degradation. That is, what is a decrease in the amount of polymeric scaffold. By that here, the decrease change is 20 minus 18 by 20. So that is 2 by 10. In fact, it's 20. Change is actually minus 2 inch percentage. This is minus 2 by 20 into 100. This is minus 10%. But they are not asking you for change percent. This is minus 10%. Degradation. By definition, how much did it reduce by? This is 2 by 20 into 100. This happens to be plus 10%. For INAT, you cannot enter a plus. Yeah, you have an option to choose a sign, negative, positive, or negative sign. So we entered, I think, minus 10 did not get any marks. Those who entered 10 got marks. What is important is you're looking for what is a decrease by using the word degradation. They add a time constant here, this becomes a first order system. How fast is this change happening? In fact, they have given you some time information. In 7 days, there is a 2% change. You simply model it as a first order system. How much change will there be in 14 days? Right? This can easily be first order transient question can easily be framed here. The first order transient question is the most important gate biomedical question, right? Notice. In this case, it's fairly easy. No transients. Although 7 days is given, that doesn't matter. Only the change matters. But this can be easily modified into order transients. This is the change is going to happen exponentially decay, and then ask you some question based on that. Notice this question is essentially that tail strength of a degradable solution is exponential, right? In fact, yeah, this is the zeroth order system. In fact, time doesn't matter, only the change matters. Quantify the change. In this question, you made it one level harder. So much change happen in so much amount of time. When will this much amount of change happen? How long will it take? Yeah, how long will it? When will 20% decay to 20% happen? And this question is actually somewhat tricky. I have already put up sort of the solution is already available, right? This is Gate PM 2020. You can find the solution. Kind of running short of time. So I cannot afford to spend a lot here, but let me quickly solve this and move on. But this is actually somewhat tricky. Tricky because you typically need 2 points to deal with a first order transient system. But what is given here is actually 3 points. And 3 points are not consistent. They are not in a single exponential curve. What I mean by that, going on as an exponential decay, typically, the starting point and some other point, you can find what the time constant is and all that, right? This point is known, time and the value is known, time and the value is known. These 2 points are known. You can, the time constant, you can find the value at any other time. You can find the, given a value, you can find the time and all that. You can find the time at any other value. Given the time, you can find, you can do all of that. So with 2 points, you can fit that exponential curve. But what is given here is actually 3 points. The initial values, things are, changes are mentioned with respect to 100. At time 0, this is 100. At 10 days. 3 is from its original strength by 40%. So what is left is decreased by 40%. So what is left is 60%. They gave you a third point. The third point, so after at 20 days, so this is of course days, and what I have here is this percentage strength. They ended up giving you 3 points, and so this happens to be at this point, this is 50. Let me also draw some guidelines. 60% at 10 days, it's 50% at 20 days. What they are asking you for, notice. The real problem here is you can fit a curve just based on 10 and 20. If you extend it, it doesn't pass through 100. It's passing through something else. Even actual data is this way. So if you extend it, it doesn't meet at 100 at t equals 0. That's a problem. So you have to kind of only deal with the exponential curve here. Exponential here, what happens before 10 days? This problem is ill-posed. There is no solution to it. There's a system of 3 linear equations. What is the common intersection point between these 3 lines? There is no common intersection point. There is no solution. Like that, given these 3 data, you cannot fit one exponential curve. System is ill-posed. So coming back to this, so now we have to deal with this. What they are asking for us, hey, when does it become 20% of the original value? This exponential thing drops. It become getting slower and slower to 0. When does it become? How long does it take? Somewhere it becomes like 20%. Question is, when does that happen? Very, very quickly. Notice change here. 30 equals 10. So we have initially 60. Let's have this in gray. Or it's 60. After some time, it became a fraction of 50. Notice e power minus delta t by tau. This is a fraction. E power minus thing is a fraction. Highest value, largest value is 1, smallest value is 0. It's a fraction between 0 and 1. And when delta t is 10, let me use a slightly better color there. Power minus delta t by tau. When delta t is 10, that actually happens to be, the fraction happens to be actually 50. Notice 50 is a part of 60. So you can find the tau. Can someone help me by finding tau here? The time constant tau. This will have units of days. Ln on both sides. Find it. Take ln on both sides. Find tau. Tau is somewhere in the power. You have to undo the power. Undo the exponential. How do you undo the exponential? Do the inverse of exponential, that is ln. So take ln on both sides. Get it to ground level. Right? Subscript, superscript. All superpowers are removed. Iron Man suit, gamma ray, every all superpowers remote, get it back to ground level by doing ln on both sides. I'm doing ln because this is e power. If it's 10 power, I'll be taking a log. Take ln on both sides. Get the value of tau. If you know the tau, notice does t. If you know tau, of course, you can find the time corresponding to any other value, right? You have the reason to find the tau as t. Again, is a fraction of this e power minus del t by tau. Sometimes it's a fraction of 60. We are interested in 20, so how long does it take? What is the delta t corresponding to that? I suppose, let me also quickly verify that. I have 0.833 minus 10 by minus 0.18. If you're writing the GATE exam, you're supposed to be doing this using a GATE calculator. So that's correct. T4 point, exponential, some of that fractions, decimals, and all that matter. So let me have intermediate value. Let me have generously 3 decimal places, 4, 8. Now I know 20, I know 60, I know this. I also know tau. At this stage, my question is, hey, find the delta t. Let's quickly find the delta t. The starting value, I know the fractional value, I know the time constant. I just need to find the time it takes, right? Change of time it takes. So quickly do that. So your delta t happens to be get us 60.25666, 60.26 days. So the answer is 60 days. No. But I used to have a teacher who would say, no. I never actually appreciated the significance of that until I kind of starting to appreciate all the YouTube tricks that makes, all the tricks used in YouTube to make students watch a particular video, right? Until then, I never appreciated that why someone has to say no as no. Some emphasis, some appeal has to be made. Some kind of ornamentation has to be done to what you have to say. I never kind of understood it, but right now I better appreciate it. Anyway, so the answer is no. What you have here is delta t. What you have here is this length delta t. Is that what they are asking you in the question? Time taken for the tensile strength to decay to 20% of its original value. Initially it's 100. How long does it take to become 20%? So that is not the answer. 60 is not the answer. The answer here is rather starting from 100%. How long does it take to become 20%? Hey, there is this delta t. And then the initial 10 days. Answer is 10 plus delta t. Kind of shown it there in the figure. So I'm not going to explain this any further. 10 plus delta t days, and that becomes 70 days. That's your answer. Notice, hey, the time constant. You could go fit this. See what is the value at 100. Time equals 0. Is it 100%? No. It'll be going elsewhere. On the same exponential curve. This curve will not touch 100 at time 0. It will be touching some other point. In fact, you have the values right. You can also actually substitute this and check that. But I'm going to skip this step right now. That's it. Let's move on. Finally, this inevitable question, at least one question, often two questions. Stress strain curve, right? We are into that. Choose the option that has the biomaterials arranged in order of decreasing tensile strength. PMMA, polymethyl methacrylate, human bone compact. Human compact bonds. There is no abbreviation for that, is it? Only PMMA is abbreviated. Fine. Orthopedic application. Not necessarily that. The order here. Yeah. Actually, I was saying few digressing on fee and all that, right? The reason I actually brought that is someone said sir, me and so listening together in one laptop, I would actually appreciate that one of you join, get your friends, and if you are learning, I'm actually happy. Somehow, in fact, I already tried to make many of this right accessible and affordable, right? Affordable, accessible, right? So more students are learning, whether live class or recorded videos or this public YouTube videos, doesn't matter. My objective is more accessible, more affordable, more students, right? More learning. That is happening, whether whether I am aware of it or not. In fact, I rather want all of you to be like sitting along with your friends. I really the links that I share, class links that I share, kind of like I don't mind if in fact, I cannot check if someone is sitting near you, right? There are instances of me actually catching some cases due to some interesting reasons, but I really don't mind. So other than that detective pleasure of figuring things out, there isn't any. I only want that to happen. You're sitting along with someone else. That's a good thing for me. Anyways, let's get back here. I just gave you some time to anyone answer this. It's fairly easy, I suppose. We have graphite epoxy mixture. Is a mixture. Our students, the mixture that shows up in their mind is a eating mixture. So this is a graphite epoxy composite. You are composing music or you are composing materials, right? So you are doing engineering like combinations of materials, hoping to get best of both the worlds, or kind of hoping to improve a hybrid version, right? So typically these composites are the strongest. Many of you chose option B, a composite degree lesser tensile strength compared to compact bone. Graphite epoxy is polymerized, it's kind of set. This is kind of like hard. This is what you typically use in bone experiments, mechanical property experiments. Epoxy is what you have at the cap, as a cap of the bone, quite rigid epoxy. And on top of that, you have added graphite, typically to make it stronger. If you answered B, can you double check your response? I thought composite going to be the strongest, hybrid version, some kind of engineering composition, not music composition, some material composition is happening, right? Composite strongest, the mixture strongest. These three order, there isn't any guess, right? The weakest is a foam. There isn't the weakest is a foam. There isn't any doubt there. But the real question is the order here. And to address that, notice you have cortical bone or compact bone. You make, hey, one of the reasons is bread. Notice the bakery bread, especially the one, you can actually take it and make it into really, really small. You can kind of compress it. You remove all the pores and all that, right? The bread actually quite big, but it weighs very, very less because it has a lots of pores, right? So porosity is something that can easily increase the size, keep other things less, like weight and all that, right? So you have the compact bone, and then you have the spongy trabecular bone, trabecular bone. The typical cement that you put in, it's often at the interface between these two, bone cement. In fact, there is also something compact here, or there is also some kind of implant, titanium or something like that, that has a similar strength as the implant. So the cement is kind of, one side it has an implant, other side it typically has a spongy bone. It has to gel well or bind well with a spongy bone, which doesn't happen if they have different thicknesses. So cement's thickness is somewhere between the polymer foam. Spongy bone is sort of a polymer foam. In fact, polymer foams based on the molecular weight, manufacturing process, and all that, it can be something like a duster, or it can be strong as a spongy bone. But very quickly, your spongy bone is over here. Spongy bone, let's say, is close to a polymer foam. Cement often has to bond or bind well with both the compact and the spongy bone. So it has strength in between those two. It has to bond on both the sides. It needs to have a similar strength. So this is between. So this order is kind of set. And I suppose the composite is really stronger. Can someone just give you 2 minutes? Can someone quickly check whether it's B or C? I'm giving the exam right now. I'm choosing C. That is, can someone go back to the answer key and check official answer key and see if it is B or C? Just make sure. Could also do that. This is 2023, is it? You got a confirmation. Yeah, it is C. This reason being simple. I suppose, see this order, this compact cement order kind of maintained in a graphite epoxy. You cannot put it here, man. This is really absurd. Okay, notice. Compact cement foam, that order is kind of preferred. Compact compact cement foam order is kind of preserved. Even here the order is kind of changed, and this is really absurd. Graphite epoxy cannot be the weakest. Even if actually if I am confused between B and C, that is understandable. This cannot be the case. Foam is not, graphite epoxy is not stronger than foam. Typically the confusion between B and C is understandable, but notice I already kind of emphasized that, right? Music composition and all. I pulled in Beethoven, music composition, your engineering materials, right? Mixtures. Typically that mixture, that engineered combination is stronger. Let's go to the next question. Based on the stress strain curve of three different materials, X, Y, Z shown in the figure, which of the following choices is correct? Titanium hydroxapatite. What? Hydroxapatite crystal, I suppose. One is a polymer. The weakest is a polymer. He has to be a polymer. It's like a rubber band. You pulling in polyethylene. Polythene paper. It's polyethylene, is it? Polyethylene. Z has to be polyethylene. I rolled out two. Is not titanium. Higher the curve here is, the more stiffer it is. So the slope tells you how stiff something is, right? Polyethylene is the least stiff. I ruled out option C and D. It's between titanium hydroxapatite and hydroxapatite titanium. One is a ceramic, another is a metal. There's a ceramic, this crystal in the bone, hydroxapatite. Suppose some calcium phosphate. And we have titanium metal. Quick exercise. What is the Young's modulus? Can all of you Google that for titanium and hydroxapatite? Hydroxyapatite. Someone likes to more water. They have an appetite for water. Calcium phosphate, no. Hydroxyapatite. I suppose there are some OH groups and things like that. So, what is the Young's modulus for this and this? Google that and let me know. Some range, approximately it's this. Young's modulus is a measure of stiffness, so slope is higher. So you can quickly try to answer whether the slope or that slope. You can compare whether initially whether the slope is higher or that slope higher. If you have numbers, you can compare. Thanks, I started getting answers. Gigapascal. For titanium, this is 120 GPa. Somewhere around that 100 to 130 and all that. For hydroxapatite, I got a 6 GPa. Probably you're not looking at hydroxapatite crystal, single crystal, which is likely to be more stiffer. One of the values that I got is 106 GPa. Young's modulus stiffness. So for crystal, it's around 100, right? Titanium around 120. Again, if you look at single crystal titanium, right? Titanium alloy is a single crystal. There are pure titanium crystal 120. At least based on this, what seems to be the case is that titanium is more stiffer. The answer based on stiffness seems to be this. So what I expected when I first saw this question, but we did challenge this question. Many students did, because the GATE committee thought the answer is B, hydroxapatite titanium polyethylene. That kind of makes sense, as let's say what we are looking at is the entire stress strain curve. That is like, this is kind of material is failing here. This material is kind of failing here. This material, notice for a polymer, you don't know whether it's kind of failing here or still going, right? But let's say it's kind of failing here. There is no confusion with Z. Then the context changes totally. What you have here is a brittle material, and then what you have here is a ductile material. Ductile. In fact, this titanium metal is ductile. This hydroxapatite crystal ceramic, this hydroxapatite crystal or ceramic, typically this is brittle. So if you go by brittleness, based on brittlity and ductility, option B makes sense. But that is not clearly shown, and also this order doesn't match with, again, the reported values kind of vary. If you look at, because the properties vary, manufacturing methods determine the properties here, what you are measuring, how you are measuring, that many of that affect. So often there is a range, but based on stiffness, most of us thought the answer is A, based on whether brittlity, ductility classification. Option B, option B. That is a gate key. Gate. And we challenge it, they didn't change it. We'll leave it at that. Let's not be aware of it. This question repeats. What should I do? I don't know. If this question repeats, at least the committee should put the endpoints over there where the material really failed. That points needs to be there. Summary, you're plotting stress and strain. Then often we are looking at stress strain as independent of geometry. Load versus deflection is dependent on geometry. This is a property that is independent of geometry. You do one experiment, you can actually apply that to any geometry. On the other hand, if you're plotting load versus deflection, for each geometry, you're doing an experiment. There are infinity of geometries, right? You run into this issue. So your stress quickly. So right now, the time is 8:45. There's a scheduled time, but I'll have to finish the stress strain. Two numericals from stress and strain. We're also going to introduce some basics on stress and strain. So we'll finish this, we'll wind up. I anticipate us likely to go till, you're likely to take 30 more minutes. Likely expect on an average, we are expected to take more minutes. I'm just letting you know that because we are at the scheduled time. So of course, I will try to make this video, recorded video available so that, we have to sign off now, we can come back and watch later. But those who are staying here, we are likely to go till 9:15. Stress strain curve. This is sigma by definition is load per unit area. Load, if we use, I suppose, force is more recognizable. Force per unit area. Strain by definition, change in length as you pull apart something, right? What is a change in length? Length, the normalized change in length, typically, let's say original length. And these two are related by, typically for most of this material, this relation is linear, at least in the initial part. Few interesting things happen later, but initially at least this is almost linear. So that slope is known as Young's modulus, correlated by this relation. And I already said this is geometry independent. So given a material, you do this experiment once in any geometry or experimentally feasible geometry, that's it. You can apply that knowledge to design and analysis of any other geometry. And materials do like this. You can take a wire and like really bend it, twist it, crumple it and all that. Stent, right? Stent is slightly different, but let's say copper wire, you can bend it. Because they have a tendency to actually, for a lot of change in length, bending correspond to actually change in length, right? There is a lot of change in length. But if you take something like a chalk piece, you try to bend, kind of bends, breaks, right? There are some materials like this. And then you take a rubber band. No, not this much stress and all that. It seems to be going to the moon. It's kind of do it this. So what I have is a rubbery or a polymeric material. There are glassy polymers, there are rubbery polymers, right? There is glass transition temperature, but there is this rubbery polymer, rubbery polymer. Some of them refer to this as hopefully not elastic polymers, elastomeric polymers. There is actually a lot of issue with problems using, at least even now, using elasticity, there is a lot of problems. So we'll stick to rubbery polymers. In a scenario, at least elastomeric polymers. These are metals that are referred to as ductile, that they change in length reasonably a lot before failing. These are referred to as ductile. And that suddenly break, this is brittle. I already saw this kind of similar strain curve. And brittleness, typically, where does this happen? This is typically a ceramic. Metals typically are ductile. Typically. Sir, titanium in room temperature, in body temperature, is it ductile or brittle? If I Google it, it says in room temperature it's brittle, right? Typical metals are ductile. Again, you can quantify ductility and all that. So there are complications involved, but typically, you have to put that typically really, really big somewhere. Color, what color? Typically, ceramics are brittle. Typically, metals are ductile. Typically, polymers are rubber. we have these three types of behavior. Notice the slope there is, at least the initial linear part is what is referred to as a Young's modulus. In a pull it apart, the simple tension experiment, that's Young's modulus. And I have also defined this, right? Let's get a little more space and write down what is what. I have the stress, I have the strain epsilon, the force or the load F. Let's say this is force is area, L, engine length, R. The length is L. So here also rewrite this. You can substitute what is stress, you can substitute what is strain, and that will look something like, I'm not going to write it, F by A equals E into del L by L. So these things, F, A, E, del L, phi are related. Even any four, you can find the other. Typically, there is a lot of a lot of questions. Almost every year there is a question based on that. Given any four, and find the other. Of course, something like area, you can get that from radius information of a cylindrical sample, or you can get that from a side information from a square sample or a rectangle sample, things like that. Given any four, you can find the other. One such example over here. And what you bare minimal thing you need to know about stress strain is here. At least I said it verbally, including why stress strain and basic things and all that. In all, biomaterial was tested for its tensile properties. The experiment was conducted using a cylindrical sample of this material, which was 10 centimeter long with 1 centimeter diameter. Tensile force is 50 kilonewton. The cylindrical sample tested along by 4 mm, cylindrical sample elongated by 4 mm based on the experimental results described above. Tensile modulus of different tissues given in the sample. Biomaterial will be a suitable replacement for. Essentially asking you the given any four, you can find the other, right? They are telling you slightly rewording it slightly differently. Is the best match, stiffness match. When they say suitable, they are telling you where is this Young's modulus match happening. Best match, best stiffness match. That is essentially what they are asking. Best stiffness match. So find the stiffness, see where it falls. And I already told you A, E, del L, L. Even any four here, A4, you can find the other. Most gate problems, if you write this set equation, you can write the terms in the equation. Then given n minus one of them, you can find the nth one. Write any nth one, right? A quick way to learn how they modify same concept, different questions, how do they frame? Yeah, in this exam, they give this 4. Next exam, they give another 4. How many permutation combination you could do? That is like, you can quickly do the permutation combination. There, how many ways you can slightly rephrase the question instead of asking what is the Young's modulus, where is the base to, what would be a suitable replacement, slightly reworded, right? You got all the questions from a single concept. Fine. Force in a slightly brighter color. Force is 50 kilonewtons is SI into 10 power 3 newtons. I'm going to get that from the diameter information over here. I already told you cylindrical sample radius diameter can get that. Diameter information 1 centimeter. So area of that is point. We write that in somewhat meter color. E r square 3.14 into r is 0.5 into 10 power minus 2 meters. Again, put everything in SI, stick to SI, you're so good. Hopefully, it's a Pascal, it's an SI. Whether what matters is whether giga or mega. This squared, if you know how to handle the squares. A. Sample elongated by 4 del L as 4. In SI, this is 10 power minus 3 meters. Was 10 centimeter long, it is 10 centimeter. L is 10. Won't get marks for this because it is 10 into 10 power minus 2. Have they given any 4? Yes. Given you F, they are given you A, they are given you LL, they are given you L. They are asking you what is this E? What is this Young's modulus? The 4 they have given you is this, right? Quickly find it. Where is the best match? If you forget the formula, let me also comma here. E epsilon. I is E epsilon. Sigma by definition is F by A. It's E into L by L. Hey, take the del L and L to that side, you got E, right? Just calculate it. L by L. Let me also make sure someone is sitting here because I am kind of going over time. Some of you are still here. Fortunately, I have this really, fortunate to have students like you. Right? Imagine someone is like taking online class. After some time, there is no one sitting on the other side, but the class is going on thinking, hey, there is someone sitting. We don't use videos because, often, at least, for our level, for our rest of the class doesn't get so much information in your face. Suppose, in fact, I conducted a poll. You get some kind of information from the teacher's face. Fine, the expressions, how you look, and all that. There is some information there, and also it kind of somewhat entertaining. So we don't have all of our videos. Often we also don't use audio that much. We typically use a chat. So none of you are sitting there. I wouldn't like recognize that. So I'm really waiting for an answer. Yeah, I kind of gave you a reasonable estimate. Okay, I'll do this once. What I am getting is a really, really large number. I did it really fast. What I got is on double confirms, I'd be good. I got 0.59 to 10 power 10. The answer should be in Pascal, Newton per meter square. That I suppose is 15.9 gigapascal. That best matches with the almost every year there is a question on this. Not a numerical, this. And this is typically the intersection of biomechanics and biomaterials. I had to save some time there, so I kind of discussed it here. And most of the things that you need to know what is what, I discussed it. What, why, and all that I have kind of put up here. Given any four, find the other. An area can be given in terms of radius or diameter or site. They want to make it really, really interesting, complicated. Now, notice, given any four, we can find the other. Given any four, let's say force area, Young's modulus L is given, you can find the change in length. If you know the change in length, you can calculate the strain. If you know the strain, if Poisson's ratio is given, you can actually calculate the lateral strain. You can slightly complicate this, right? And those things are kind of discussed. Hey, how is shear modulus, Young's modulus, Poisson's ratio? How are these three related? What is Poisson's ratio and all that? I already discussed that in the mechanics revision video. I'm not going to repeat that again here. But that is a link. They can slightly make it more complicated. Given any four, find the other, they can slightly complicate it. But that's only a slight complication. If you know what is what, it's fairly easy. That brings us to the last question. Temperature of woven cement is increased from so cement thickness is this. Just developed to, actually this is a thermoelastic material, somewhat reasonably old. I don't want to get into the theory of this thermoelastic material. Very briefly, sigma is E is proportional to, there is thermal strain, there is strain, there is elastic strain. It's proportional to elastic strain. Elastic strain is essentially difference between total strain and thermal strain. And because the way the cement is sandwiched here, I suppose the total strain is zero. There is thermal strain. Because of that, notice total strain is zero, but thermal strain is non-zero, because of which you can have a stress. I think the thermal strain is fairly easy, I suppose. By definition, strain is change in length by original length. We are talking about the specific change of interest here as the thermal change in length. If you know the temperature difference of temperature, thermal expansion coefficient, linear thermal expansion coefficient, area expansion coefficient, volume expansion, whatever some one of that is given, calculate del, right? Del L, call this coefficient alpha. This is notice it. I can actually, even if you don't know the relation, I can write it down based on the units. Per unit degree Celsius, this much change, right? That is typically, so what you need is a change in length. So take this alpha, multiply by del T, multiply by L, you get change in length. This is the thermal change in length. Just calculate this value. So alpha is, this is 90 into 10 power minus 6 into delta T. 10 minus 37, I suppose that is 50. Length. And thickness is the length. Cement is being sandwiched between the bone and the implant. Thickness happens to be the length into mm, so 10 power minus 3. Here it is 90 micrometers. This is, so it's either this or this at this stage, or this. So actually to answer, we have to actually find the stress. Some of you might be wondering, let me quickly write down LS, 10 power minus 3. Delta TS 37, 87 minus 37, that is 50 degrees Celsius. Alpha is kind of given over here. I have written that in meters. And right now your stress sigma equals, Young's modulus is given. Yeah, modulus is given. This is 3.5 gigapascal. So that is 3.5 into 10 power 6. Hey, kilo giga mega. And then deci, centi, milli. micro, nano, pico, femto. I suppose all of you know this, what this giga, mega, diga, and all that, right? This is Pascal. I have that in SI. Oh, the change in length, I just found it, right? So this is 90 into 10 power minus 6. That is the change in length. The original length is 20 into 10 power minus 3. Yeah, epsilon t. What I have here is epsilon t. This is essentially E. Calculate this. I suppose I have it by 20. Or I'm missing. No, I'm correct. This happens to be 15.75 megapascals. I'm getting at that as 15,750. That is it. I'm missing a somewhere. I'm missing a unit somewhere. Yeah. While I was lecturing you on kilo, mega, giga, femto, deci, centi, that and all that, I made a mistake here. While writing it down, giga is 10 power 9. That should get you 15.75 into 10 power 6 and get the answer. So is 10 power 9. Fair. So this is done. Hey, what is this thermoelasticity? I know I cannot. I already told you what you need, but just complete this stuff. Figures. Take a sample. You apply your force to the sample. It kind of changes its length. There is a mechanical change in length due to mechanical effects. This change in length can be positive or negative, and decrease its length. So if it's a compressive force, this have some reference lengths. There's an increase in length. There is a decrease in length there. This is a sample. And this is mechanical force. The thermoelastic material, all it says is can change in length to delta T. Delta T can be positive or negative. So technically, based on your reference temperature, there can be an increase or decrease in length. What this is minus delta T. That's it. This is purely thermal. Now, can the sample can apply both mechanical force. There is a change in length due to that, and there is a change in length due to temperature. So I heat it plus I pull it. Scenario is possible. Notice there is a very, very, very peculiar scenario where I pull it and I cool it down. It need not have a change in length. There is both mechanical force, mechanical stress, as well as a thermal stress, the thermal strain and thermal stress. This is a scenario where I have minus F and delta T. Either I can compress it and heat it, or I can cool it and put a tension. In both the scenario, there is a very specific, interesting case where there need not be a change in length. Compression is not clear, so I'm going to put double arrows to note that. Either this and there is a tension and you're cooling it out. If you do it, there is a very peculiar scenario where there need not be any change in length. In fact, the reason to discuss this is this peculiar question, right? This question actually seems to be the fourth category drawn here, which exactly brings me to the likely time that I said we'll finish. Bottom line, this thermoelastic question is somewhat relatively advanced, certainly more advanced compared to stress strain. Notice all we are still doing is stress strain, somewhat more advanced. But the essence, you really need to know, and all the complications going on here in this question, the sandwiched bone between the implant and sandwich cement between the bone and implant, all the complications, I have indeed actually explained it to you. That information is over here. May not be in a digestible form or a approachable form in one viewing, but that information is over here. And what the question is essentially telling you this bit. Quickly wrap up. And so that brings us to the end of biomaterial discussions. More importantly, we have finished shaping, biomet. Right now, if you actually know what I have discussed in and out, all the variations and complications that I have discussed in the revision videos, if you are following that, if you can do that, if you can solve similar problems, plus of course aptitude and math you can clear. You shouldn't be really bothered about it, but we of course want to shine. So I'll follow up with bioenst medical imaging, but these are actually weightage is much higher. I would need about 2 weeks each, which means we'll take about a month from now to get these, but I'll get that to you. Bioenst and medical imaging. The moment we get there, you know that in and out, you are confident. Should be a gate biomedical exam should be a piece of cake. And this includes APTI, and math. So that brings us to a very nice end, and I'll see when I can make this available to you. If there are no other questions, I think we are already over time. Let me stop all these things. Thanks for staying back, those students who is here. Walala Madhu, Shamayata, Guru, Purna. Thanks for staying back. Hey, one of the things is beyond whatever I said, okay, if you need me to know, this is somehow I managed to find time, resources, and all that to actually keep this program running, or whatever I could contribute, right? I can keep it running. Most of your fees and all that is actually going towards, making this knowledge accessible, approachable for as many students as possible. That's where most of your, if I am spending time specifically for certain students, whatever you kind of like pay as a tuition or fee, that is going towards reaching more students. And yeah, having said that, what if you want me to actually, already I'm spending a lot of time. On top of that, you want me to spend more time, right? Of course, that is going to cost you. And also the point is, I have made it as reasonable as possible. Having said that, let's get back to biomaterials.